Hi, in the previous lab tutorial in lab 5A, we noticed some lane cover misclassification which were caused by spectral confusion. This is the lane cover map that we created in lab 5A. As you can see, there are some areas here which are misclassified as built up areas, but actually these areas are bay areas or some cropland areas. So this is these are the cases where we have a spectral confusion between the built-up class and the Bay Area class or the cropland class. Right. So the focus of this tutorial is to try to improve lane cover classification by combining optical data from Sentinel-2 with the synthetic aperture radar data from ALOS PALSAR-2. We hope to reduce the spectral confusion and capture more lane cover information. Okay, so the dataset that we're going to use here is the ALOS PALSAR-2 ScanSAR, which is available in Google Earth Engine catalog. So this dataset is actually the first L-band synthetic aperture radar. So this is the PALSAR-2. So it is on board the ALOS-2, which is the Advanced Land Observation Satellite, which was designed by the Japan Aerospace Exploration Agency, JAXA. So this dataset is good for wide area monitoring. So ALOS PALSAR is available 25-meter resolution, the one which is in Google Earth Engine catalog. So this is just a normalized backscatter data, and it is usually in the range between, for this study area, between 0 and 8,000, which is the data set in 16-bit mode. So for the purpose of this class, we will normalize it between 0 and 1. Right. So and this tutorial, the only change is that adding the ALOS PALSAR dataset. So I'm going to focus on that as much as possible. But the rest of the code is similar as in the previous tutorial in lab 5A. Right, so we, as usual, we start by just installing the datasets, installing the libraries that are not pre-installed in Colab. So for this case, there are Stereo and EarthPy. And we import all the libraries that we are going to use, as we have done in the previous tutorial. And after that, we are going to mount our Google Drive so that we can access the datasets in Google Drive. So make sure that you have authorization to access your Google Drive. And then, as we have done in the previous tutorial, we are going to define the path and the variables. So the path is where the datasets, that is our datasets, are stored. So for my case, in the sample path, I have the training dataset, which is in .csv file. And I also have the Sentinel-2 image, which again is stored here as a GeoTIFF. So remember, I've shown you a video where I've created this dataset during the data preparation. So that was the data preparation lab. And then I've added the PALSAR dataset, the ALOS PALSAR-2 dataset here. And we are just going to use the HV polarization dataset. Right. This part, I'm going to leave the link to the code where you are going to see how you can compile the ALOS PALSAR HV polarization imagery in using Google Earth Engine catalog. Right. So this code showing this will be in the description, so you can access it and then try to run it. Right. After that, we are going to define the target and predictor variables. Okay. So for our predictor variables, they are the Sentinel-2 bands from band 2 to band 12, and then I've added here HV. So this simply means the ALOS PALSAR-2 dataset, which is HV, horizontal and vertical polarization. And then our target here is the land cover class. Okay, it's the land cover classes. So these are the land cover classes: bare areas, built up, cropland, grassland or open areas, woodland, and then water. And then, as we've done in the previous tutorial, we have defined the palette and also the colors for the different land cover classes. So next we are going to load the images using Rasterio. So we are going to load our Sentinel-2 imagery, and then also we are going to load our ALOS PALSAR HV image, HV polarization image. And then just make sure that these two images match. So we are going to include this line of code to check if the image sizes are the same. Right. After that, we are going to display the Sentinel-2 imagery and the ALOS PALSAR HV backscatter image. As you can see, these are completely different. But these two imagery, the optical and the ALOS SAR dataset, really complement each other, because for the cases of the bare areas or the cropland areas, the backscatter values are quite different from the built-up areas. So this is important when we want to minimize the spectral confusion between classes that may appear similar. So in this case, the bare areas and the built-up areas or cropland areas. So to get more information about this, we have a paper that we published in 2019, I think. I'm going to leave the link of the paper so that you can get more details about this for the study area. Please take note, I'm using the ALOS PALSAR here in this case because for this study area I didn't have access, we didn't have access to Sentinel-1 imagery. So Sentinel-1 SAR data is not available for this study area for this period. Okay. Right. So next we are going to load and prepare the training data. So again, this is just taking the CSV file that contains the training data, and then we just define our predictors and target variables as we have done in the previous tutorial, and then we split the dataset into training and test data. So 70% of the training areas go for training the model, and then 30% goes to validate the model. So these are the datasets, the variables in the datasets. So we have the Sentinel-2 bands, and then we have our ALOS PALSAR HV polarization dataset here. So you can notice that I've also normalized this. This is between 0 and 1. And then we have our lane cover classes from 0 to 5. So this is just how they are labeled. Right, next we specify our random forest model here. This is just a simple model. We are just taking like 100 trees, and then we, after specifying our model, we create an evaluation model. So this is just for evaluating the model. And after running this, we can see that the accuracy is improved compared to the previous tutorial, that is in Lab 5A. So in Lab 5A, we had an overall accuracy of about 83%, while here we have an accuracy of about 86%. So it's a 3% improvement. After that, we are going to save the random forest model. So in this case, we are going to create a kind of a library where we save the model parameters. So save the model itself, the RF model that we have trained, and then the predictors variables. So these are the features, the bands that we've used, and then the label, which is the target. These are the length cover classes. And then we can create a model path here where our model is going to be saved. Right. Please take note, I'm just using the joblib library here to save the trained model, so that we can use it for future prediction tasks. For example, if we want to use this model to predict another imagery, or for other deployment purposes that we may need to use the model for. Okay. So we are going to reuse this model later, for example, when we want to perform explainable machine learning in order to understand, or in order to get into insights into how the model performed. Right. So the joblib this is just a Python library used for saving and loading Python objects. So especially large objects like trained models. Okay, so trained models, trained machine learning models. So this is a very useful for saving scikit-learn machine learning models, so that you can reuse them later. Right. After that, we are going to do the classification as we have done in the previous tutorial. Okay, so here we are just going to use the trained random forest model in order to predict the class labels for every pixel of the Sentinel-2 imagery and the ALOS PALSAR image. So before we do that, we are going to combine the ALOS PALSAR imagery and also the Sentinel-2 imagery, so that we have one object, we have one combined object which we will use to do the length cover classification. Following that, we are going to reshape this object, the combined object that contains the Sentinel-2 imagery and the ALOS PALSAR. Okay, so remember, this is very important because scikit-learn expects 2D array for prediction. Okay, so this should where each row should correspond to a pixel, and each column correspond to a band. Right. So after reshaping, we use the random forest model to do the prediction. So this is our random forest model that we are going to do the prediction on the reshaped objects, that is the Sentinel-2 and the ALOS PALSAR dataset. And we are going to save the new classification as an unsigned integer 8, because these are going to be discrete classes. Right, then we run the prediction, and then after that we are going to reshape the prediction back to image. So this is critical. We are going to shape the prediction back to image so that we can visualize the lane cover map. And then this code is just visualizing the lane cover map. So this is the lane cover map that we have generated, or that we have created using Sentinel-2 and using the ALOS PALSAR-2 HV polarization dataset. But as you can see, there's a lot of improvement. The confusion between the cropland, sorry, the built-up and cropland is significantly minimized, and also we have also minimized the confusion between built-up and some bay areas, but here it appears also there are some areas that are creeping in. But in general, these approaches quality is improved the lane cover classification map. So this is quite good. Right. So after that, you can export the map, and then you can visualize it in any GIS software. All right. So this was just this tutorial. So we can see that by integrating optical and SAR data, we can improve lane cover classification accuracy, and this is quite useful. So this approach is useful. So you should try it in your study area. So please check the full code in the description, in the video description below. So you can get this code in the video description, and also I told you can get the code also for preparing the ALOS PALSAR dataset using Google Earth Engine catalog. Right. So in the next video, we're going to use the random forest model in order to model above ground biomass density with a scikit-learn again. So this is also going to be very useful since we are using the scikit-learn library. So stay tuned.